view on xy coordinates. So in this figure we see that your r is the radius of curvature and d theta is the included angle of the segment. So your length ds will be given as r into d theta. Let this be equation 1. Now since this arc segment is very small, it can be considered to be hypotenuse of right angle triangle PQM as shown in the figure. So we draw enlarged view of this triangle and let theta be the angle of this segment PQ. So now the slope of this beam segment PQ could be written as theta is equal to dy by dx. Let this be equation 2, where your dy and dx are projected length of arc segments PQ in y and x direction respectively. Differentiating this equation 2 with respect to x, we have sec square theta into d theta by dx is equal to d square y by dx square, or sec square theta into ds by r into 1 by dx is equal to d square y by dx square. So we substitute this in place of d theta by dx, since we know d theta is equal to ds by r from equation 1. So in place of d theta we substitute ds by r. But from triangle PQM we know that ds by dx is equal to sec theta. So substituting ds by dx equal to sec theta in this equation, we have sec cube theta by r is equal to d square y by dx square. So we can write d square y by dx square is equal to, now writing for this sec cube theta as 1 plus tan square theta to the power 3 by 2 upon r. Now for beams, usually r is very large as compared to beam span is also very low. So the slope of beam, which is given by tan theta, is also very low, of the order of 0.001 radian. So we see that 1 plus tan square theta to the power 3 by 2 could be considered as simple one by neglecting this tan square theta term, since the square of this very small value will also be very small. So this expression could be written as d square y by dx square equal to 1 by r. Now let this expression be equation 2. Now combining equation 1 and equation 2, we can write d square y by dx square is equal to 1 upon ei by m, since your r is ei by m. So we can write ei into d square y by dx square is equal to your m. So this expression is called as governing differential equation of beams. An important point to be noted is that it takes into account the effect of bending moment only. Now since the effect of shear in deflection is very small, and so it is safely neglected. So we have this governing differential equation of the beam. On integrating this equation successively with respect to x, we get slope and deflection equation. So upon first integration, we get the equation as ei dy by dx equal to integral of m dx plus c1, and this equation is called as slope equation due to the presence of the term dy by dx. Upon integrating it further with respect to x, we get eiy equal to double integral of m dx plus c1x plus c2, and this equation is called as your deflection equation. And in this equation, your c1 and c2 are constants of integration whose value is to be found out by boundary conditions of the beam. Thanks for watching in 5 minutes.